the white paper of Cassandra. Uh, Here we'll be understanding how the storage system actually works in Cassandra and how why it was like built for. So the problem description say that it was mainly built because the Facebook needed an inbox search mechanism where the write throughput was very high because people around 2008 this paper was published, I guess. So in that time they had around 250 million users, and each users were published like writing so many messages. So the write throughput in that case was requested was very high. So that was one of the requirement. And yeah, the functional requirements was like should be able to handle the high rate throughput, and the system was acceptable if it was eventually consistent, but it must should have been highly available, right? The as you can see, it should be highly scalable, and the robust load balancing and the membership of nodes should be considered. And then there is another non-functional requirement was like failure detection and recovery, and replica synchronization and partitioning should also be considered, right? This Cassandra database is a lot similar to Dynamo, I would say. It inspires a lot. Even the creator, that Avinash Lakshman, is also has also worked on Dynamo, so it is highly inspired from Dynamo. This API, Cassandra provide the API is like very minimal, very simple APIs. One is like insert, which will take the column family name, which is table, and then key, partition key, and then the mutation itself. And similar in the get case, you can get the column, whatever columns that you would like, and you need for that you need to provide the table name and the key. So it is a since it is a wide column store, here it one might be confused by looking at the schema visually that it looks a bit like relational databases, but it is not, since the each row can have varying number of columns. And the table may look familiar to relational databases, but the number of columns can change in each of the rows. So that's what it makes this Cassandra is non NoSQL, where the structure is not consistent throughout the rows in the database. And that's what makes it very interesting to work with. Even though programming model that is provided by Cassandra is a structured query language, but yeah, it is a bit different. So yeah, so one of few the data model will try to understand the Cassandra that provides. It has few things like cluster, which is a group of nodes in one particular cluster, and then the key space, which is like the namespace that you need to give for each of the space, and then the replication factor. So this is fixed. The key space is fixed during the creation, and replication factor during the initialization you need to provide, which remain static. And then the column family, which is nothing but the table itself. Okay, here you need to provide the partition key and the clustering column is similar to the sort key in the Dynamo, so it is similar to that. And then the row itself, and the column. So each column, when the mutated, it will also store that its timestamp and the value and the name. So, and the super column, which is now deprecated, but earlier version had this super column. Okay. So you can say a super column is like group of all the column families. Okay. Yeah, coming to the high level design, the high level architecture that Cassandra followed. Although there were, as we saw in the non-functional requirement, there were a lot of requirements were there, but let's focus on three key things that Cassandra provides. The first is like partitioning, the sharding mechanism, and then the second is replication, and the third is membership. So in the partitioning mechanism, we'll see like similar to Dynamo, it also follows this consistent hashing approach. Not consistent, not simple consistent hashing, modified consistent hashing, which was needed because a simple consistent hashing will doesn't take into consideration for the capability of nodes, because capability of each of the nodes can be different because they use commodity hardwares which has like heterogeneity in their capacity, right? So you could say like the the modified one provides a enhancement into the simple consistent hashing, where it keeps into consideration like where this particular node, if that is very efficient, where this should be allocated. And also like load distribution was one issue in the simple consistent hashing. It is said that like the new node which is joining the cluster can be allocated to any random position, but the load aware or maybe much more efficient approach would be that if we are aware of the where the which node is more heavily affected or maybe hot, in that case there it is much it makes much more sense to add that node in that particular position, so that it can share the load between both of them, right? So as we can see in the below diagram here, we can see like key 1 is being mapped to this particular partition, and this particular partition is being assigned to node A as we go clockwise in consistent hashing, right? So let's suppose node A goes has very high overload or becomes hot. In that case, let's suppose we need to add another node, let's suppose B for example. Then if you are trying to add B over here, uh, then it must share the load in between that, right? So this particular partition will get split into two parts, similar to B tree, and this half of the partition will remain in the node A, but half of the partition which should be given to node B will happen a transfer from node A to node B, right? And this transfer happens through kernel to kernel copy mechanism. And initially the kernel to kernel copy using kernel to kernel copy mechanism, it provided a speed of 40 mbps, which later on by tuning that Cassandra teams like enhanced it a lot by using the multiple thread and like multiple other nodes which were available. Using that parallel processing, they enhanced this speed a lot. So yeah, this similar mechanism is used by P2P tools like BitTorrent. Okay. And yeah, so here in the consistent hashing, if you are not aware of it, like how it works, I would highly recommend to check it out, other videos, how the rebalancing of nodes happen when a new node joins or when a node leaves, how the rebalancing will happen. Yeah, next let's go into replication, how that works. Here the two key things here is like a replication. In the replication is read and write. So let's focus on the write. What happens in write is like whenever you invoke a write request, it goes to a coordinator node, and that coordinator node will maintain its replicas, right? So it will forward that request to replicas as well, and when the majority of the replicas uh, acknowledge that the write has been appended, then it returns a success. right? That particular write has been become successful. And in the read request, that is a very interesting part over here. This can be configured, the number of majority nodes, the number of nodes which must acknowledge that the data is correct, or maybe returns the latest data, is can be configured. So let's suppose if you want a really highly available system and you don't care about much consistency, and it's okay for you to accept a still write, a still read sometimes. In that case, you can make r equals to 1, where the number of nodes which returns correct output, correct data is 1. In that case, you might get a stale data sometimes. But if you want really a highly consistent system, then in that case you need to make the number of nodes, which is r, equals to more than majority of the nodes, right? More than half of the nodes. In the replication, we also need to keep in mind that Cassandra also provide two types of replication. One is rack unaware. It means that all the replicas will be present on the same rack. Okay, and in this case, like, the replication happens in the, like, let's suppose you have selected replication factor of 3, then other two replicas will be part of the same cluster and they will be part of the same rack. So next two successors will be selected from the ring, and then they will be replicated over there, they will be appended over there. But in the another mechanism, where is like rack aware and data center aware, in these two mechanisms the replication happens cross cluster. And in this case, what's going to happen is like, it uses zookeeper in that case for the coordination, and zookeeper will have the configurations for other cluster and where all these other replica in other cluster is lying. So in that case, the coordinator can take out the configuration, from the for the other replicas, and then it can forward the request to replicas in other cluster or other data center. And then either it can do async replication, where it doesn't wait for other replicas to acknowledge, or maybe it can do the synchronous replication. Synchronous replication could introduce a little bit of latency, but uh, it's much more like, it will be very consistent in that case. Here it talks about like preference list is it's selected in such a way that the replicas are present in other clusters. Yeah. Let's also talk about the membership. Yeah. So this membership is nothing but what happens when a node joins the cluster, or maybe or leaves the cluster. And also, like, it's possible that when a node is present in the cluster, it goes down. Then how the other nodes will be aware of that, how the coordinator will be aware that the replicas are down or other nodes are down. Or maybe let's suppose a request comes to node A, and but that that is not the coordinator for that particular key. In that case, it needs to route that request to the responsible node, right? And let's suppose that node is down. In that case, we need to have a mechanism to detect the failure, that the node is down or not, right? And if the node is if that particular coordinator is down, in that case we can return a error, right? So what happens is, like, any of the node can accept a request, and if that is a if that particular node is the coordinator itself for that particular key, then it will just return the response. Otherwise it route that request to the responsible node, get the response from there, and then forward it back to the client. So it can also act as a mediator of that request. So it is very important to detect the failure of nodes. So what Cassandra does to detect failure is it uses accrual failure detection. Not, it doesn't simply maintain a boolean flag for each of the node, that each of the node present in that cluster, that it either it is up or down. Instead, it uses this phi value for accrual failure detection. What this phi value does is like it so since we are aware from the Dynamo, you might have also seen that Dynamo also uses gossip protocol to exchange the communication, that the heartbeat communication, right? So each of the node keep sending the heartbeat to another nodes in the cluster, and that heartbeat happens over UDP protocol. So and each of these heartbeat will have a timestamp attached to it. So each of the node which is, let's suppose, take example of node A, which is accepting heartbeats from node B, C, and D, then it will maintain a sort of a sliding window of all the timestamp distribution, right? And using that distribution, it computes the phi value, accrual failure detection value. And if the phi value is like 1, then there is high chances that the conflict will occur. Means that uh, that that particular node might be down, or maybe some of its replicas are down. So or maybe a certain latency has been introduced in that particular uh, node. So that also keeps it comes into consideration using this methodology. And using this we can identify like shall we proceed with the routing or not, right? So, and if phi equals to 2, it means 1% chance that the conflict will occur, and phi equals to 3 is very minimal, and so on. So if higher the phi value, it means the better it is to route the request, or lower chances that the node is down. And once we have detected the failure, it is what we require is recovery from that failure, is right. So let's suppose a particular node is down, or and all of its replicas are down. So whenever a write comes, so this is similar to what Dynamo does. Is like, since it is a highly available system, the Dynamo is highly available system, it always accepts writes. Even all of its replicas are down, it will accept writes. And what they do is like, once the responsible node, which is maintaining all the data from a particular range, a particular partition, that comes back online, the handoff of that remaining data, the node, whatever node that was online when the responsible node was offline, that took the writes, will hand over all these data to the node, responsible node. That is not called hinted and handoff. And this hinted handoff is done using this anti-entropy mechanism, which is subtle but mechanism, right? So this is how subtle but mechanism works. Is like all of these nodes maintain the version of the data, and then once they exchange the gossip, and then they calculate the difference between the data. Whatever difference the version difference they have encountered, only that data will be exchanged, not other data. So that is the beauty of this subtle but mechanism. You can also say like Merkle tree is somewhat does the same. So yeah, I need to explore the Merkle tree part, like what it actually does. I'm not sure about that. If you can read more about it. Let's dive deeper into like how they did it in production and how the actually the storage data storage happens. So let's suppose you have just started the this complete cluster which is new. So initially there will be few seed nodes, so which are always which must be available online, and you must be sure like they are very important nodes. In that case, seed nodes maintain the routing information of other nodes as well. So let's suppose when a new node A joins and there is a seed node B already present. So node A will gossip to node B and ask for all the routing details so that it can start sending the heartbeat. So seed node will send the routing information, and then gossip using gossip protocol, node A will also maintain that same routing table in itself. So it happens, and also this cluster configuration is stored in the zookeeper. So if someone, let's suppose, wants to remove the node, or maybe do some manual rebalancing, or maybe some config changes, they can use the CLI to modify the cluster configurations, right, using zookeeper. Now let's dive into like how actually this storage works. So typically similar to Dynamo, it first stores the data into commit log whenever the write comes, and then it stores in the mem table, which is this LSM tree, and then this LSM tree flushes in a period of time. It flushes that tree structure into sorted structure into SS table. So this SS table will always contain the sorted data, and even though in the background a thread runs which does the compaction along with it as well. So the compaction happens in a way that read and write doesn't get blocked. And this commit log purging, we have also talked about how the time to time this commit log will be removed, deleted, because if the data has already been stored in SS table, then we don't need that same data in commit log, so it get purged in a regular interval. So as you can see, there is a fine line, dotted line separating SS table and commit log, which indicates that these two components are part of the disk, the physical disk which is being stored. So this data is not getting lost even though the node crashes or something. But this part of the data, which is mem table, this is stating that this data is stored in memory, so it might get lost. So that's why the data first is written into commit log, so that even though node crashes and comes back up, this mem table can be constructed from the commit log. So that was about the write. And what about the read operation? So in how the read operation happens is like, read operation will check the mem table if that particular data is present or not. If it contains that data, then good, it will return from the in memory itself, so that is fast. But if it is not, then what happens is like it goes into this second level, which is like it has Bloom filter for each of the blocks, data blocks, right? And Bloom filter will indicate that that particular key is present in that block or not. So it scans the blocks, and then if the data is present, then from that particular chunk this data will be retrieved and uh, returned to the coordinator. So that's how read happens. Now let's also talk about the really interesting part of the Cassandra, that it, it is using various modules in each of the node. So as we are aware that each node has its attached disk as well, and each node has its running various modules as well. So there are few modules like partitioning module, which is aware of like all these ranges that is taking care of, and all the, and let's suppose it needs to partition the data or maybe hand over some data, so that's this module is taken care of. And the membership module, it handles all this routing information, taking the heartbeat from the other nodes. And then also let's suppose some request comes, then it needs to route the data as well. So this routing happens over TCP, and the gossip happens over UDP. And the failure detection module that we talked about is using the UDP, right? Because this will keep happening. It will keep taking the heartbeat information and keep calculating the phi value using the sliding window, right? So this happens, and then storage engine uses TCP because it should not lose the data that it needs to write over the disk. So it uses the TCP protocol. Now let's talk about performance tuning. That is very important in production. So let's suppose you want a very high throughput from the system. In that case, you can tune in for the async replication, where you don't wait for all the replicas to reply for acknowledge that the write has been successful, and you just even though even the coordinator writes itself to the data, and it will guarantee that it has been it has request uh, made the request to all the replicas to append the same entry to itself. So it will not wait for the response. So in that case, sync replication can be used. And the otherwise, by default, the sync replication will be used, where the coordinator waits for all the replicas to respond and acknowledge that the write has been written successfully, completed successfully. In that case, it will there will be a bit of latency, but the system will be very consistent, and the data will be it will guarantee that the write has been written successfully, completed successfully. Yeah, here it is talking about the commit log purging. So as we talked, like it needs to in a regular interval it needs to be purged, right? So it maintains 128 MB size of commit log, where it contains a segment, header per commit log file. So each head this particular header will have a bit vector, and each of the bit represents the column family. So each of the, so let's suppose you have various column family in your storage database, right? So it's possible that certain let's suppose there is one column family like payments, another one is orders, and then another one is like users, and you have there recently there was mutations across these three column family, these three tables, right? So in that case, if some data is already present in commit log, but it has not been written into SS table. In that case, first you need to check if all this data has been written successfully in the SS table or not, right? So that's why this bit vector is used to indicate that all these column family has been updated. Once all the bits are set to 1, means all the column family has been updated. In that case, in that and only case, that particular logs will be purged, will be deleted from the commit log. And yeah, let's also talk about the SS table. Since SS table, the data written into SS table is immutable because it is appending to the file itself. It is also called write ahead log. So it is just appending the file, and these are immutable. So whenever you are performing any mutation to the, it is creating a new entry, new append log will be there. So that's why you always have a fresh data, uh, and also compaction is also happening in the background. So there is no lock is needed because you are not updating that same appended log, because each mutation is creating a new log. So that's why there is no lock is needed when you are reading or writing the data into Cassandra. So that's what makes it very highly performant. Yeah, so that was all about like how it stores the data. And this is a very interesting point that I noticed in the paper, that in production, they when they started earlier, in the earlier phase, they were storing all these messages in MySQL database. So while migration, they used MapReduce to run the job to migrate the data from MySQL to Cassandra. And for the observability, they since they during when this paper was written, they mentioned that it was around 150 nodes at that time. So they needed a way to monitor all these storage and the nodes, right? So they use this Ganglia tool for that, for managing the JVM performance and the CPU utilization and the storage as well. So yeah, that was all about it. Uh, that was all about Cassandra. Hope you liked this. I would recommend to go through the white paper as well, and this is a sort of like what I found interesting in the white paper. So I would attach the link to white paper as well in the description. If you found this video very helpful, then please do like. Thank you.